Good morning. Today we are going to take up our last lecture in the topic of amorphous solid dispersions. We are going to discuss about the decision trees that are followed in the pharmaceutical industry for the development of amorphous solid dispersions. This flow diagram gives us the pathway which is followed by the pharmaceutical industry for selecting a amorphous solid dispersion. Our primary aim is to find out the optimal polymer which will help us in achieving the desirable properties in the amorphous solid dispersion. The first starting point is asking a question: can amorphous API be prepared? This means that can the pure API be converted into a relatively stable amorphous form? If the answer to this question is yes, then you can investigate the physical stability of the amorphous API, and if found suitable, you can directly use the API in the amorphous form for the product development, which we have discussed is very rarely the case because most of the APIs in their amorphous form are going to be unstable. If they are unstable in the pure amorphous form, you then need to go to the next question. Can an amorphous dispersion with acceptable physical attributes be prepared? If you don't get the appropriate physical attributes, then you continue your dispersion attempt. But if you are able to get the appropriate physical attributes, you need to then ask the next question: does the amorphous solid dispersion have acceptable apparent solubility? Means, is it giving you the desired solubility benefit that you want to achieve from the amorphous solid dispersion? If it doesn't give you the acceptable solubility enhancement, then you continue your investigations and try to find some more optimal polymers for the purpose. If you get the appropriate apparent solubility, then the next thing to be evaluated is, does it have acceptable stability? And if the stability is not appropriate, then you will investigate approaches like giving a protective packaging or protecting your product during the processing. If it gives you the desired stability profile, then you need to check whether the process can be scaled up and formulation for administration, which means is the scalability there in the process or not. If it is not scalable, the attempt would not be acceptable and you will have to find another process which is scalable and commercially applicable. If the process is scalable, then you go to the evaluation of the in vivo performance, and if you get the proper in vivo performance, then that would become your final amorphous solid dispersion candidate. If it does not give you the appropriate in vivo performance, you will only keep this as the secondary approach and investigate some other approaches which might be more appropriate for your molecule. That means you will have to investigate some of the alternate approaches like nanocrystals or lipidic systems for delivering your molecule, as you found that the amorphous solid dispersion was not giving the desired in vivo bioavailability advantage. This slide captures one decision tree that has been proposed by Hoffman La Roche, innovator company, for screening the polymers for the amorphous solid dispersion. The entire approach is called as screening of polymers for amorphous drug stabilization, and it has been abbreviated to SPADS. In this particular approach, you again ask certain question: is an amorphous solid API dispersion necessary? If the answer to this is no, then you evaluate different other formulation approaches. If the answer to this question is yes, then you conduct the dissolution assay wherein you first take more than or equal to 7 polymers as the stabilizers, and you investigate it at 3 to 4 drug loadings. DL stands for drug loading. So this will allow you to estimate the supersaturation potential of the polymers. The polymers that give you the desired supersaturation potential will be carried forward for further evaluation. The next question in this decision tree is, does the polymer provide improved API dissolution, solubility, and or supersaturation? If you are not getting the desired advantages, then you evaluate different other polymers till the time you get the appropriate polymer for the purpose. If you get the desired solubility advantage, the next thing that you need to assess is the drug polymer miscibility and the physical stability of the amorphous solid dispersion, which can be done either by conducting microscopy based imaging assays or by conducting the interactions assay to find out the drug polymer interactions. In the imaging assays, we are primarily looking at presence or absence of birefringence, which is because of the crystalline particles. And if the birefringence is absent, we can safely conclude that your drug is in the amorphous form. So this can be used as a way of assessing the physical stability of your amorphous solid dispersion, either in ambient conditions or on accelerated storage conditions. For this study, you use 3 to 6 polymers at 2 to 3 drug loading. We are reducing the number of polymers and the drug loadings so that we are now going to reach to the optimal polymer and the optimal drug loading. The next question that we need to ask is, does the API polymer combination have molecular interaction? That is API capable of forming hydrogen bonds and there is acceptable miscibility and stability between the drug and the polymer. If you don't get this, then that particular polymer is not going to be suitable for your given API. And if the answer to that is yes, then assessment of process solid dispersion is taken forward. And in this case, you are going to narrow down to 1 to 3 polymers at 1 to 3 drug loadings. So you can see that we started with more than 7 polymers initially and 3 to 4 drug loading, and we have sequentially reduced the number of polymers and the drug loading to reach to the optimal polymer and the optimal drug loading. We are now going to discuss something about the manufacturing techniques that are used for the amorphous solid dispersion. In the previous 2 slides, we discussed about the lab scale screening of the appropriate polymer and appropriate drug loading for the amorphous solid dispersion. The next step obviously would be the manufacturing of the ASD. There are 3 techniques which are mentioned in the literature that are used industrially. The first one is the hot melt extrusion, and the second one is spray drying, and the third one is co-precipitation. The first two, that is hot melt extrusion and spray drying, are the most common techniques that are utilized, whereas co-precipitation has been used very rarely for the industrial scale-up of the amorphous solid dispersions. Hot melt extrusion is a solvent-free technique wherein you take the mixture of the drug and the polymer and pass it through the hot melt extrusion equipment, and you get the pellets of the amorphous solid dispersion. The hot melt extrusion is not applicable to drugs that have high melting point, that is greater than 200 degrees Celsius. In those cases, there is a possibility of degradation of the polymer or discoloration of the polymer at these high melting points. Also, it is many a times difficult to achieve the required drug polymer miscibility when the melting point of the drug is on the higher side. Spray drying basically uses a solvent system for dissolving both the API and your polymer in a common solvent system, which is then spray dried. And it is applicable only when the drug has solubility in one of the organic solvents that is acceptable for spray drying. Sometimes it happens that the drug may not have the required solubility in a spray drying acceptable organic solvent. In that case, you will not be able to exploit spray drying as the possible manufacturing technique for the amorphous solid dispersion. Couple of products in the market have also been introduced using co-precipitation, especially one product by Hoffman La Roche company was commercialized based on the co-precipitation technique, and it is applicable for drugs that have high melting point and have low solubility in the common organic solvents. These types of API will not be amenable for hot melt extrusion or spray drying technique. Hence, co-precipitation was developed as an alternate technology for commercialization of those APIs. We select the appropriate manufacturing technology based on the dose and the melting point of the API that we are trying to incorporate into the amorphous solid dispersion. This is a comparison of hot melt extrusion technique versus the spray drying technique. In the hot melt extrusion technique, solubility or miscibility of the API in polymer is crucial. In the case of spray drying, drug and polymer should be soluble in an acceptable solvent system. Melting point in the case of hot melt extrusion should not be more than 200 or 225 degrees Celsius. And in the case of spray drying, solubility in one of the solvent is critical. Particle size of API is crucial for complete melting of the API in polymer when you are passing the material through the hot melt extruder. Here the particle size is not crucial in the case of spray drying because you are going to dissolve the entire API in the solvent system. Plasticizers are sometimes included in the HME process to bring down the processing temperature of the mix of the API and the polymer. In the case of spray drying, solvent itself acts as the plasticizer for the solid dispersion and brings down the processing temperature during spray drying. For HME, you require several grams of material for the lab scale development. For spray drying, you only need 50 to 100 milligrams of the material, as it is possible to generate very small batches in the spray dryer. The equipment footprint in the case of HME is small, whereas the equipment footprint in the case of spray drying could be large. Solvent cost and recovery are not critical factors because this is a solvent-free method, whereas in the case of spray drying, this is going to be an important consideration. This is the cross-sectional diagram of a hot melt extrusion machine, wherein you feed the API and the polymer through this particular opening, and it goes into the hot melt extrusion, which has the arrangement to increase the temperature as well as to provide shear with the help of a screw-like arrangement inside the hot melt extrusion. The first zone is the melting zone, where the drug and the polymer will be taken beyond their glass transition temperature and melting point respectively, which means the glass transition temperature of the polymer has to be exceeded so that it will reach into the supercooled liquid state, and in that supercooled liquid state the API will dissolve or it will get miscibilized at a reduced temperature, which means well below the API melting point. This phenomena of mixing of the API with the polymer shall take place. This is because of the fact that there is a melting point reduction when the API is miscible with the polymer that has been taken. And after this mixing or miscibilization has taken place, you will get a homogeneous discharge from the opening, wherein it is going to be cooled and it will come out in the form of the pellets. These pellets can then be used for either compressing into the tablets, or they can be filled into the capsule dosage forms. This is the diagram of the spray dryer. In the spray dryer, as we mentioned, first we have to dissolve the drug and the polymer in a common solvent system, which is then fed from here through a nozzle and converted into a spray with the help of the pressurized air. This is called as the drying chamber. Here we introduce hot air to remove the solvent from the droplets, and these droplets, after getting dried, depending upon their particle size, if the particle size is more, they will settle down in this collector. Otherwise, they are going to be carried through this opening into the collector, and they will get collected here. There is a continuous application of a vacuum at a particular value to allow for the drying of the particles and continuous removal of the solvent. The applied vacuum also helps in taking the particles for the or the dried particle into the collection chamber. Let us now discuss something about the practical considerations in the stability of the amorphous solid dispersion. Drug loading is an important consideration. More the drug, the greater would be the probability of its recrystallization, because the interactions that happen between the drug and the polymer are important for keeping the drug in the amorphous form. As a rule of thumb, storage temperature should be Pg minus 50 to decrease or lower the molecular mobility of the glassy state of the API. This is also called as Pg minus 50 K rule. K stands for Kelvin. Supersaturated ASDs tend to destabilize due to the greater chances of homomolecular interactions, that is drug-drug and drug-polymer, drug-drug and polymer-polymer. This should be polymer-polymer interaction, which can result in higher molecular mobility and nucleation. We had also discussed this earlier, that there could be formation of drug-rich and polymer-rich zones in your amorphous solid dispersion, which can act as a precursor to the nucleation of the drug, leading to its crystallization. Drug loading should not be higher than the miscibility of the drug polymer system. If you go beyond this value, there will be a greater tendency of the drug to recrystallize from the amorphous solid dispersion. To formulate stable amorphous solid dispersion, the drug polymer miscibility regime must be studied to predict the drug loading levels in the polymers. This is a case study of 139 compounds that were formulated as spray dried amorphous solid dispersion with a polymer called as HPMC-AS, and this diagram gives us the relationship between the Tm by Tg versus log P for 139 compounds that were studied. On the x-axis you have the log P value of the API that was taken, and on the y-axis you have the ratio of Tm divided by Tg, which means the melting point divided by the glass transition temperature ratio. If the ratio is higher than 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, we'll see how it affects the stability of the amorphous solid dispersion. Similarly, how does the log P of the API that was taken for designing of the ASD affects the stability as well as the dissolution rate that is achieved from the amorphous solid dispersion. In group 1, we have cases where you can achieve greater than or equal to 50% loading in the solid dispersion because of the high Tg value of the API. Higher the Tg of the API, less would be the need for the polymer concentration to stabilize the amorphous solid dispersion. Unfortunately, these are very rare cases that we encounter practically, because the ratio of the Tm by Tg is not usually in this particular range. Group 2, which is shown by this region, contains a drug loading of 35 to 50%, and this is the typical solid dispersion range, which means this is the typical range of the API that is loaded in the solid dispersion. And in this case, the Tm by Tg ratio is somewhere around 1.3 to 1.4. In fact, there are many candidates which will show you a ratio of higher than 1.4, and it can even go up to a value of 2.0. Group 3 are the compounds that will show 10 to 35% drug loading in the solid dispersion, and drug will have a propensity to crystallize, and that may be the limiting factor for achieving the higher drug loading. As I told you, there are going to be many drug candidates which will fall in this zone or maybe even beyond this zone, since they will have a Tm by Tg ratio of up to 2.0 or even higher. If we look at the impact of the log P on the performance of the amorphous solid dispersion, as the log P value increases, the dissolution rate from the amorphous solid dispersion will decrease because of the greater lipophilicity and poor solvation potential of the API per se. And this gives rise to group 4 of the ASDs, wherein you can only achieve 10 to 30%, 10 to 35% drug loading in the solid dispersion, because if you increase the drug loading, you will not be able to achieve the required increase in the dissolution rate. Effect of moisture has been discussed in the earlier classes as well. Water is a very potent plasticizer for the amorphous form, and this can cause a decrease in the Tg value and thus increase the molecular mobility, which will lead to the reduction in the physical stability of the amorphous solid dispersions. Moisture can also disrupt the interactions between the drug and the polymer, resulting in phase suppression, which will be followed by crystallization of the drug in the ASD. Relatively less hygroscopic polymers like methacrylates, and HPMC-AS are thus used to help in the stabilization of the ASD by minimizing the moisture ingress into the amorphous solid dispersions. We'll complete the lecture with the help of a case study of the amorphous solid dispersion. This particular work was carried out in our lab in the NIPER and involves the drug celecoxib and the polymer PVP, which were converted into a amorphous solid dispersion. Spray drying was used for generation of the amorphous solid dispersion, and the mechanisms of amorphous stabilization were found to be anti-plasticization, which means increase in the glass transition of the glass transition temperature of celecoxib because of its miscibility with the polymer, and since the polymer has a higher Tg value, the overall Tg of the amorphous solid dispersion was much higher than that of the drug alone. And this is shown in this DSC heating curves, wherein you can see this is the Tg of the celecoxib alone, which was somewhere around 56 to 57 degrees Celsius. The black curve shows the Tg of the polymer, that is PVP, which is around 169 or 170, and the red line shows the Tg that was obtained with the drug polymer mixture, and the ratio here was 4:1, which means 4 parts of celecoxib and 1 part of PVP. And you can see Tg value, which was midway between the Tg value of drug and the polymer, was achieved in the case of amorphous solid dispersion, which will obviously tend to stabilize the amorphous form of the drug. Specific intermolecular interactions were also found out between celecoxib and PVP, and with the help of FTIR and molecular simulation studies, we were able to find that there are specific interactions between the CO group in the polymer and the sulfonamide group of the celecoxib. Both these things, that is the antiplasticization and specific drug polymer interactions between the drug and the polymer, led to reduction in molecular mobility. And if the molecular mobility decreases, the amorphous solid dispersion will have a greater physical stability and a lesser tendency of recrystallization. The dissolution advantage from the solid dispersions is shown in this particular diagram. This is the value that you get with pure crystalline celecoxib, which is around 3.5 micrograms per ml. With the amorphous celecoxib, which means you are just taking neat amorphous celecoxib, there is a very marginal increase in the solubility benefit, and it then tends to fall back to the solubility of the crystalline form, which means there is a very small increment in the solubility, and also this small increment is very transient, and you tend to get back to the solubility of the crystalline form. If you keep on adding increasing amount of PVP at 5%, 10%, 20%, 40%, and 60%, you see improvement in the solubility of celecoxib. Interestingly, the maximum solubility that we get was with 20%, and if you go beyond that concentration to 40 and 60%, no additional benefits were seen in the solubility of the celecoxib. Based on this study, the concentration of PVP was selected as 20%, which means the system was 80% celecoxib, 20% PVP, which also can be mentioned as a 4:1 ratio of the drug and the polymer. We then included another third ingredient in the amorphous solid dispersion, which means in the PVP and celecoxib system, we included meglumine. Meglumine is a amino sugar which has also the property of creating a basic or alkaline microenvironment. Celecoxib has a pKa value of 11.1 and is a weakly acidic drug. By including a alkalinizer in the formulation, we were able to achieve the enhancement of the solubility by two mechanisms. One was based on the alkalinization of the microenvironment that led to the increase in the solubility of celecoxib. The other one was through the uh, optimal contribution of meglumine to the thermodynamics of the amorphous solid dispersion, which led to the further stabilization of the amorphous solid dispersion, and that was also responsible for increasing the aqueous solubility. The thermodynamic parameters like heat of solution were also calculated, and it was found out that meglumine contributed by reducing the heat of solution in the amorphous solid dispersion. This sky blue color curve indicates the solubility that was achieved from the binary system, and this pink color graph shows the solubility that was attained from the ternary system. So there is almost a double increase in the solubility of the celecoxib by inclusion of meglumine, and meglumine was included in the concentration of 10%. So now the composition of the final ternary amorphous solid dispersion was 7 parts of celecoxib, 2 parts of PVP, and 1 part of meglumine. The meglumine was found to act as a stabilizer as well as a solubilizer and provide synergistic advantage in the solubility of celecoxib. The bioavailability studies confirmed the findings of the solubility study, wherein this was the curve that was achieved in the animal bioavailability study, this sky blue color curve from the binary system, whereas there was a very significant increase in the oral bioavailability for the ternary amorphous solid dispersion. If we look at the relative bioavailability from the uh, binary and the ternary system, in the case of the binary system, almost 206% increase over the crystalline celecoxib powder was shown or was observed, whereas in the case of the ternary amorphous solid dispersion, a 3 times or 3.1 times increase over the crystalline celecoxib powder was observed. There was a significantly higher Cmax and AUC and lowering of the Tmax from the amorphous systems and especially from the ternary amorphous systems. The characterization tools that are used for the amorphous solid dispersions are captured in this slide. We can use XRPD, DSC, hot stage microscopy, spectroscopy like IR, solid state NMR, and Raman, and moisture uptake studies by dynamic vapor sorption for the characterization of the amorphous solid dispersion. And these are the specific uses or instances where these techniques are utilized for the characterization of the amorphous solid dispersion. Summarizing the take-home messages from the amorphous solid dispersion lecture, amorphous systems can provide higher solubility as compared to their crystalline counterparts, which can be theoretically calculated by using the equation proposed by Parks and co-workers. However, experimentally determined solubility values are usually less than the predicted values. This reduction is due to water-mediated supersaturation and recrystallization of the amorphous drug. The solubility advantage gained from the amorphous systems can be improved by adding crystallization inhibitors, which are mostly polymers, to the formulation to get ASD. ASD amorphous systems can be stabilized during shelf life and dissolution by preparing the ASD with polymers. ASDs stabilize the amorphous drugs by 4 mechanisms: anti-plasticization of the drug, intermolecular interaction, reduction in the molecular mobility of the drug, and reduction in the chemical potential of the drug. With this, we come to the end of our lecture on amorphous solid dispersion. We are now left with another lecture on the particle level of the solid form, which we shall be taking in the next few days. And with that, we will be completing our coursework on PE 660, that is solid state pharmaceutics. If you have any questions related to this lecture or any topic related to the amorphous system or amorphous solid dispersion, feel free to post your questions on the WhatsApp group. Thank you very much for your attention, and we hope to meet again very soon in the next and the last lecture for solid state pharmaceutics.